All right, so today I'm going to be going over some formal charge and hybridization. All right, so formal charge is the characteristic of an atom to, in whether or not it is more positive, meaning lacking electrons, or more negative, meaning it has more of a surplus. All right, it's the character of the charge of the atom itself. All right. And so, first and foremost, there is a formula for that, and it is as follows. So, formal charge equals the number of valence electrons minus half the shared electrons minus half, oops, half unshared electrons. All right. To me, I don't like this formula at all. To me, it makes me think of fractions, and I don't like fractions. And so this is the way that I like to approach it. So formal charge equals the number of valence electrons minus the number of bonds that are being made minus the number of lone electrons. All right. Essentially, sticks minus dots, with, of course, valence included. All right. So here's a little example. All right. How about the formal charge on the sulfur? All right. So first and foremost, we should be familiar with the number of valence electrons. And this basically associates with the group number that the atom lies in. All right. And so as of right now, or you know what? How about this oxygen? Because that is a super common atom that's used in Orgo. All right. So the number of valence electrons on that oxygen possesses is 6, minus the number of bonds that it's making, which would be 2, 1, 2, minus the number of lone electrons. How many dots is oxygen possessing? 4. Get 0. So that oxygen is neutral. That is a neutral oxygen. All right. And so something that a pattern that I would like to share is how many bonds that a atom would typically make in order to be neutral. And as of right now, we know oxygen would and when it makes 2 bonds, it is neutral. All right. How about fluorine? In order for fluorine to be neutral, it needs to be making 1 bond. Nitrogen is pretty common. Nitrogen would be making 3 bonds if it's neutral. Carbon would be 4. Boron um, would be 3. And hydrogen, of course, it only has the capacity to make 1 bond. All right. And so if you have this in mind, then you can at least get halfway there in terms of eliminating answer choices because most of the time our exams are multiple choice. All right. A pattern that I would like to show or reveal bouncing off of this is oxygen. So oxygen making 2 bonds is neutral. All right. What if it makes 3 bonds? It would be positive. What if it's making 1 bond? It would be negative. Let's show this. All right. So let's say we have what we would call a carboxylic acid. And remember, in order for oxygen to satisfy a Lewis structure, it has to have a full octet All right, so if it's making one bond, you draw out the three lone pairs. All right, so let's do the formal charge of that atom. So oxygen has 6 valence electrons. We get that from the periodic table. Minus one bond that it's making. Minus how many lone electrons does it possess? 6. 2, 4, 6. What do we get? Minus 1, which checks out, right? If oxygen is making one bond, and it does in fact satisfy a Lewis structure, then it would be negatively charged. How about if it's making 3 bonds? Right? And let's just say the rest of the parent chain you can kind of make up as you do practice. All right. So that carbon is making a triple bond with the oxygen. All right. Right now it doesn't have a full octet. We need to show that it in fact does. All right. And so how about the formal charge on that oxygen? So oxygen has 6 valence electrons minus 3 bonds that it's making minus 2 lone electrons, which gives us a +1, which checks out. All right. And so that is a very easy pattern to recognize when you're looking at molecules. If you see an oxygen that's making one bond, it's negative. If you see a oxygen making 2 bonds, it's neutral. And a oxygen making 3 bonds is going to be positive. All right. So that's the formula for formal charge. These are how many bonds has to be made in order to be neutral. And here is a extremely common pattern that I want you guys to recognize when looking at oxygen. So with that being said, you should immediately look at a bond line formula or any molecule that has an oxygen on it and be able to automatically tell without having to do the math. You can obviously use the math to double check it, but you don't need to if you recognize that pattern. All right. So let's do a few examples. All right. So how about this oxygen? All right. So we see that that oxygen is making 3 bonds. So we can automatically assume that it's going to be a +1 charge. But if we wanted to double check it, we can. All right. 6 minus 3 bonds minus 2 lone electrons is going to give us +1. How about carbon? All right. That carbon is making um, uh, is making 4 bonds. All right. Carbon has how many valence electrons? 4. How many bonds is it making? 4. Does it have any extra lone electrons? No. It's going to give us a neutral carbon. How about that oxygen? All right. Oxygen has 6. How many bonds is it making? 1. And how many lone electrons does it have? 6. And that's going to give us a -1 charge. So as of right now, despite there being charges, the overall charge of the molecule is neutral. They cancel each other out. All right. How about this carbon here? All right. Carbon has 4 valence electrons. It's making 3 bonds minus 2 lone electrons. So that looks like it's going to have a -1 charge. All right. How about the nitrogen? All right. Nitrogen has, nitrogen has 5 valence electrons minus 4 bonds. All right. And as of right now, it has a full octet. it doesn't have any more lone electrons on it. 0. So we get +1. All right. So as of right now, this molecule would be neutral because those two cancel out. All right. How about that carbon? All right. 4 minus 2 bonds minus 4 lone electrons. I believe we get -2. How about the sulfur? Sulfur has 6 valence electron that's making 4 bonds. All right, and as of right now, doesn't have any lone pairs. Has a full octet, giving us +2. How about this nitrogen? Nitrogen has 5 valence electrons, making 2 bonds minus 4 lone electrons, giving us -1. All right. So hopefully that makes sense. And this one is just another example. We're not going to go through that, but you would go through the same exact process. All right. And so how about let's just label some of these. All right. So how about this oxygen on number 4? Number 4 oxygen is making 1 bond. So we know that's going to be a -1 charge. That nitrogen is carrying two two bonds. All right, so we automatically know that's going to be, like what we just did up here, -1. That fluorine, remember that pattern that I spoke about earlier, that is going to be neutral. All right, a nitrogen carrying or making 4 bonds is going to be positively charged. All right, and so on and so forth. So hopefully it makes sense, this pattern and the utility of formal charge. And again, if you're looking at an atom with formal charge, you can automatically assume or begin to think about, is it lacking electron character, or does it have a surplus of electron character? And so you'll see an acid base like that nitrogen can act as a base or a electron donor because it has an excess of electrons that it possesses because it's negatively charged. So it can use those to give away and bond with something else. All right, so that's some formal charge for us to use, think about, and hopefully it makes sense in terms of the approach. All right. Now I wanted to talk a little bit about hybridization. All right. Here's this table we're going to think about. All right. So for something to be sp3, it needs to have 4 groups. sp2 is going to have 3 groups. sp is going to have 2 groups. All right. And so the geometry of sp is going to be linear. sp2 is going to be trigonal planar. All right. And sp3 is going to be tetrahedral. All right. So here's an example of linear. All right. So that carbon there has how many groups coming off of it? This carbon group here and this carbon group here. 2 groups gives us linear. All right. sp2, here's a common example. All right. So that carbon there has how many groups coming off of it? Oops. 1, 2, 3. All right. So it's going to give us sp2 and be trigonal planar. All right. And so on and so forth. I don't know. Let's just make something up about that carbon. How many, how many, not bonds, how many groups are coming off of that carbon? One, two, three, four. Not bonds, groups. All right. As you can see, that double bond is a group. And same goes for lone pairs, which is what we're going to, in which I believe I have a couple examples. All right. But let's just continue to fill out this table. All right. Tetrahedral is going to give us a 109.5 angle. That is the most ideal situation for a carbon, which is what we love in organic chemistry. All right. Trigonal planar is going to be 120, and SP is going to be 180. All right, so let's do a couple examples. So you should be able to, from Gen Chem, piece together some Lewis structures, but we're gonna go from formula to Lewis structure. All right, so this carbon has 4 groups, so it's going to be sp3. That's going to give us a tetrahedral shape with 109.5 degree angles. All right. How about CH3 plus? Right. That plus indicates that there's a lack of electron character, right? So we wouldn't add a lone pair in that case. All right. So carbon is making how many groups? 1, 2, 3. So 3 groups, which would provide us sp2, which would give us a trigonal planar shape at a 120-degree angle. All right. How about CH3 minus? That minus, it does indicate that there is a extra pair of electrons there. All right. How many groups do we got going on? So that's a group, that's a group, that's a group, and so is the lone pair. Okay. That needs to be considered into the number of groups. All right. And so this is 4 groups, which would give us sp3, and that would provide us the same information as we as we already know of now. All right. How about this one? This one's a little odd. All right. Hybridization of that carbon. How many groups are coming off of it? 1, 2, 3. sp2. All right. So a lot of this is pattern recognition and repetition. All right. How about this one? So that is just a horrible drawing. How many groups are, I still have this drawn wrong. Pardon me. All right. So how many groups are bonded to, or not bonded, but how many groups are coming off of that carbon? 1, 2, giving us sp. All right. Now with that, let me just give a little weird example. Right. about that oxygen? All right. Or you know what? How about this carbon? Because organic is all about carbons. How many groups are coming off of that? One, two, sp. All right. Um, but this one, all right. So again, let's look at the pattern involved that we've been looking at several times now. So how many groups are coming off of that carbon? One, two, three, giving us sp2. And how about that carbon in the middle? How many groups are coming off of that? One, two, giving us sp. All right. This ketone here, a ketone will be another video. But how about that carbon? How many, not carbons, but how many groups are coming off of it? One, two, three, giving us sp2. All right. So hopefully that begins to cement itself. A lot of it takes pattern recognition. All right. But hopefully, if you can use a table like this to apply it, then it can be applied elsewhere. All right. So here's some examples. All right. How about let's just start with number one. So how many not bonds, but groups are coming off of that carbon? One, two, three. Well, number one is sp2. How about that oxygen? All right, how many groups are coming off of that? Let me make this a little thicker. One, two. Remember, lone pairs are considered three, four. So this would be sp3 being four groups. All right, I think I skipped one over here. How about this carbon number two? How many groups are coming off of it? One, two, that's it. It's going to be sp. This oxygen number four, all right, it's going to be one, two, three groups, sp2. How about that carbon here? What I like to do when sometimes things are too shortened upon, and it's sometimes, at least initially, in terms of learning something, I like to draw the whole thing out. So that carbon is as follows. H2. Okay, so the hybridization of that carbon there in the center, how many groups are coming off of it? One, two, three, four. It's going to be sp3. All right. Lastly, how many groups are coming off of that? One, two. That's going to give us sp. All right. And so hopefully that begins to again cement itself. And hopefully that provides a nice overview. And as you can see, I'm not one to get super granular and into all of the orbitals and stuff like that. That's the physics. I'm not a physics guy. I'm just here to share what is needed to solve a problem, period. All right. You can cut through all that. And if you are interested in that, there is your textbook. There's other people that are super into the physics to explain the whys of hybridization and formal charge like that. But hopefully, this provides a brief, succinct, but to the point overview of formal charge and hybridization needed in order to solve some of your fundamental problems in Orgo. All right. Have a good one.